Good day, folks. This is the work energy and power question. This is the Eastern Cape June 2022 paper. Now let's cut the chase, guys. It says a mining trolley of mass of 540 kg moving to the left. Here's a mining trolley. Approaches point A. Here's point A. Before that, with a velocity of 12 meters per second and come to rest at point C. So the trolley moves all the way up until point C. If you see BC, it's an incline. Now it says AB is rough while BC is frictionless. That means these are two systems. This system is closed, right? It's closed because there's no friction here. It's frictionless, right? Now AB, it's open because it has what? It's rough. It has a friction. Now the coefficient of kinetic friction between the trolley and the rough surface AB, it's 0.8, which is the mu k. The description of the surface here, it's 0.8. BC is 4.5 long and makes the angle of 7.5 with the horizontal shown in the diagram below. So if you look at this point BC, we're given the displacement there that the trolley moves. That's the displacement, right? And the angle, we're told it's 7.5. So when the trolley reaches point B, C, right? It reaches point C with the velocity, which is the final velocity, is 0 there because we are told it comes to rest at C, right? And another thing that is important, at C it has a height, right? Which is the height final. Here at the bottom is the height initial, right? So the velocity that reaches point B, it's going to be the initial in this track. It's going to be the initial in this track, and that will be the final. And the initial we do not know because it starts there with a velocity of 12 meters per second and goes that way and reaches that point with another velocity. So this will be the initial velocity of this track, and here this will be the final. But when you between these two in this track, this will be the initial and this will be the final velocity. And from in this track, so at this point it will be the initial same velocity that it reaches there, it changes to be the initial and that to be the final, right? One thing that I want us to look at before, in this system here, we are not given the height, we're given the angle and the displacement. We're given the hypotenuse and the opposite. So one of the trig ratio that we're going to use there is sine. Sine, it's so, which is opposite over hypotenuse. So it's sine 7,5 equal, the opposite is going to be the height, and the hypotenuse will be the displacement, which is 4.5. And then the displacement there, the height, is going to be equivalent to sine 7,5 degrees times 4.5, right? That's the height. It's going to be in meters there. Okay, now let's answer the question. State the principle of conservation of mechanical energy in words. The principle of conservation of mechanical in words, it says total mechanical energy in an isolated system remains constant, right? Total mechanical energy in an isolated system remains constant. Now they ask you the principle surely in the next question, and they want you to use the principle. They said use the principle of conservation of mechanical energy to calculate the velocity of the trolley at B. So we want this velocity. It comes with that velocity at 12 there, and then it moves in that track until it reaches B. We want that velocity. So it won't help us to use this system or this track to get this. The way that is easy to calculate that velocity is this track, because we want this velocity, which is the initial, and we'll use the final there, the final velocity. So we qualified to use the conservation of mechanical energy here, even if they didn't tell us, because this is a closed system, this track. Why we can't use it here is because this is an open system. In an open system where there are conservative forces like friction, we cannot use the conservation of mechanical energy. We can only use when it's closed. So let's do it. So the mechanical energy at B is equal to the mechanical energy at C, because the system is closed. So the mechanical energy here is equal to the mechanical energy there. So this velocity that we want, where is it? It's at B. So the gravitational potential energy plus the kinetic energy, which is half mv squared. This is at B. And then the mgh plus half mv final at C square. And then we substitute. When we talk about B, we're talking about this point. At B, since there's no height here, guys, so the gravitational potential energy will be 0. You put the mass and the 9.8 and the height is 0. So everything here will be 0, right? And then the kinetic energy there, the kinetic energy here, we do have the velocity there, because it's the velocity, is the final velocity of this track. When it starts there to there, this will be the final velocity. So it's the one that we want. So we put the mass there. The mass of the trolley, it's 540 V initial of B square. And then there at the top at C, we're talking about this. So the final, the height there, it's this, right? It's this, that's the height there. So what are we going to? We're going to put the mass, it's 540 times 9.8, and the height there, we already done it. So it's going to be sine 7.5 degrees times 4.5 plus the velocity at point C, at point C there, the velocity there is going to be 0. That means the kinetic energy there is 0. So this kinetic energy there, it's 0 because of because of the velocity that is 0. So we'll just put 0 there, right? So half times 540, it's going to be 270 initial VB square, and then we'll be left with this. So when I punch that in the calculator, that will be 3,108,3507, and then we divide by 270, and then we put the square root. So if I punch that in the calculator, I put the square root this, it will be the final velocity there, it will be 3,39 meter per second. This is the velocity at this point. So surely it means that the velocity as it moves here in this track decreases due to friction and air resistance. So it reaches this point at the velocity of 3,39. Right? Now let's go to the next question quickly. The next question, it says calculate the kinetic frictional force between the trolley and the rough surface of AB. So we want the friction here. Remember, we were told that this is rough, it has a friction. So in order to do that, since we're given the mu k of that track, which is 0.8, so we can easily calculate the friction by using the formula. Friction is equal to mu k times normal force. And then the mu k is 0.8 and the normal force is equal to mg. So it's going to be 540 times 9.8. That's mg. So punching that in the calculator, you get the answer. That is 4,233.6 newtons. That's the friction, that X there. Now the next question, 8.4, it says state work energy theorem. Guys, when it comes to definition, it's exam guidelines all the time. So the work energy theorem, guys, it starts from knowing the definition, the formula. It says work net is equal to change in EK. That's the formula. So you can define the formula from seeing there. You can define the work energy theorem from seeing the formula. It says the work net on an object is equal to the change in kinetic energy of the object. You see? Okay, let's leave that. Now let's go to 8.5. The question, it says use the principle of the energy principle only to calculate the work done by friction as the trolley moved from A to B. Guys, it says energy principle only. You cannot use any other thing than the energy principle. Now the energy principle that you're going to use here, it's the work energy theorem, which is work net is equal to change in momentum. So the work net here, it's going to be the sum of the work done on an object on the track AB. On the track AB, you need to know what is the force acting here. The only force that is acting here while it's moving here is friction. So here you have the work done by friction, right? And they want the work done by friction. And then the change in kinetic energy, we know it's half mass times final velocity minus initial velocity square. And then we substitute. We have the mass is 540 of the trolley, and the final velocity at that track. This is the final velocity. Remember, I said at B is the final and this is the initial. So the final velocity here is the one we just calculated. It's 3,39. So it's 3,39 square minus the initial, it was 12 square. So if you punch everything in the calculator, the answer that you should get there, it's supposed to be negative 35,777,13 joules. Guys, surely you should have anticipated that the work done by friction, it should be negative, right? So guys, you can use even the work done by non-conservative force, which is a work energy theorem, which is, it gives you the same, which is this. It gives you the same. But now, here's the catch here. Since this is a flat surface, it has no height. So here, the change in gravitational potential energy, it will be 0. So you'll be left with the EK. And then the work done by friction, then the work done by non-conservative force, it will be the work done by friction. So do you see, it gives the same, thing. So you'll be left with change in kinetic energy and the work done by friction, the same thing. So it's the same thing as this one, right? Let's go to the next question. The last question, it says the distance from point A to point B. So what is required here is this distance from here to here. What can we take an advantage of to give you to calculate that distance? We have to use the friction. What exactly in friction that we can use? We can use the work done by friction, right? We will say work done by friction is equal to friction times displacement cos theta. Okay, why are we using this one? The work done by friction we have, we want the distance, which is the displacement, and the angle there, since the friction, it opposes the motion, the trolley is displaced this way and the friction is going in that way. So the angle is going to be 180, right? So let's substitute there. So the friction, we calculated the friction. The friction, it's 4,233. 4,233,6. Am I right? Yeah. Times by the distance, which is the displacement, cos, since I said it opposes the motion, cos 180. And then the work done by friction, we just calculated here. It's negative 35,777,13. So if we divide by 4,233,6 times cos 180, which is -1, cos 180, and we divide in this side by that, 4,233,6 times cos 180. So this and this will cancel. You'll be left with the displacement. The displacement, or the distance that it covers from point A to point B, it's 8,45 meters. This is the displacement. Distance or displacement from there to there. They said distance. That's it, guys. I hope that makes sense.